Welcome to Study Loop.
This is Chapter 22, Problem 16 from the Sears and Zemansky's University Physics textbook. Some planetary scientists have suggested that the planet Mars has an electric field somewhat similar to that of the Earth, producing a net electric flux of negative 3.63 times 10 to the 16 Newton meters squared per Coulomb at the planet's surface. Calculate the total electric charge on the planet, the electric field at the planet's surface, and see the charge density on Mars, assuming all the charge is uniformly distributed over the planet's surface. All right, the first thing that we need for this particular problem is some astronomical data. So we looked that up, and I've drawn a crude picture of Mars. And the astronomical data we're going to need is going to be the radius of Mars, which is 3.39 times 10 to the 6 meters. So that's just something we look up in the front cover of the textbook. And we're given that the flux is negative 3.63 times 10 to the 16 Newton meters squared per Coulomb. So what that means is because this flux is negative, then the electric field must point towards the center of Mars. So we have the electric field is pointing down towards the surface, so coming in from space and pointing down towards the surface. And we're also going to need, as we get through this problem, we're going to need epsilon naught, our universal constant that shows up quite frequently in electrostatics of 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. So part A is using Gauss's law. Gauss's law simply says that the total net electric flux is equal to the total enclosed charge divided by epsilon naught. We know what the flux is, and we know what our universal constant epsilon naught is. So then it's just basic algebra. Rearrange this to solve for the total enclosed charge Q is just the flux multiplied by epsilon naught. And that gives us the total enclosed charge is negative 3.21 times 10 to the 5 coulombs when we plug in the value for the flux that we're given as well as epsilon naught. Part B asks us to find the electric field at the planet's surface. So with this, we use the definition of electric flux. The definition of electric flux is the electric field times the surface area times the cosine of the angle between the normal to the surface and the direction of the electric field. In this case, since the electric field is pointing down towards the surface, and the normal to the surface, though, would point straight up out of the surface. So the angle there is 180 degrees because of this. So our angle phi is 180 degrees. And we're assuming that Mars is a perfect sphere, and the surface area of a perfect sphere is 4 pi r squared, where r is the radius. Well, we already looked up that data. So we can use the definition of flux, and we arrange this to solve for the electric field. Just a little bit of algebra, and the electric field is the flux divided by the surface area times the cosine of phi. And we just plug in, instead of the area, we make the substitution of 4 pi r squared times the cosine of phi in the denominator, and we still have the electric flux in the numerator. So we plug in our value that we're given for the electric flux, as well as our astronomical data that we looked up for Mars. So we take our value for r, and we plug that in. And we take 180 degrees, plug that in for phi, and we get the electric flux to be 2.51 times 10 squared newtons per Coulomb as our final answer for part B. Part C asked us to find the charge density on Mars, assuming the charge is uniformly distributed. So the charge density, denoted with the Greek letter sigma, well, that's just how much charge is distributed over the total surface area. So we just take our total charge, Q, and that's the total charge that we just found in part A, because that's how much total charge is on Mars. Take this divided by the total area, the total surface area of Mars. Total surface area, again, is just 4 pi r squared. So our total charge density is just Q divided by 4 pi r squared. So we plug in, again, Q from part A, as well as the radius of Mars that we looked up, and we end up seeing that the charge density, then once we put these numbers into the calculators, negative 2.22 times 10 to the negative 9 coulombs per square meter. So we see, even though the charge is fairly large, 10 on the order of magnitude of 10 to the 5 coulombs. It's spread out over the entire planet's surface area, so the charge density is very small, being on the order of 10 to the negative